I see you made it back. Well, I'll try to give you as much information as I can before Megastrain comes down upon us. So, we're dealing with our all stress cube, and our stress has three-dimensional attributes, right? We have normal stress and shear stress in the X, Y, and Z planes. Now, we can simplify this a little bit. So we say that for many cases in engineering, we'll have the opportunity to use what we call plane stress. So what is plane stress? Nah, it has nothing to do with airplanes and flying. What plane stress is means that all the stresses act in a single plane, right? So one plane of our block, so maybe the XY plane is what we're going to study. Now, why do we study this? Well, it's very applicable. So I want you to think, I like to use the example here of the wall. You can see the wall is big. It has forces acting on it, even if we had some earthquake or lateral wind forces or something, a big storm's coming. It would have shear stresses, and it has forces up and down and everything, but everything's happening in one XY plane. Does that make sense? I think we could come in here and we could pull our block out, and we would see that on the surface here, there's no stress on the surface. The only way there would be stress on the surface is if I was actually physically pushing there, or there was something pressing or some pressure there. So we see that when we pull this block or this element out of our wall, this surface has no stresses. Namely, there's no stresses on it in the normal direction, so acting out or pressing in on it. And there's also no shear stresses. So no shear stresses, no tau Zx or tau Zy. Alright, so if we do that, we can reduce our general state of stress from 9 components down to 6 components. This applies to many situations. We can see even in our car, for instance, much of the surface of the car is not subjected to constant stress. So in a lot of engineering applications, frames, beams are another great example. We might have loads on the beams, they might be bending, we have all kinds of things happening, but these elements here, as we look at them, there's no pressure, there's no horizontal pressure pushing on them, there's no forces that are acting in that direction. So beams are another great example where we commonly see plane stress able to be applied. Alright, so let's go ahead and write down a definition for plane stress and go ahead and sketch the plane stress element.
When we talk about plane stress, we're talking about stress that's only acting in one two-dimensional plane. So we'll consider stresses acting only in the XY plane. Again, this is common for many engineering scenarios, and it'll help simplify our calculations if we're able to eliminate some of these stress components. Now, inherently, getting rid of the z-plane gets rid of the 3 stresses on that particular surface. But remember, if the stresses are to be all in one plane only, we can't have tau xz or tau yz either. So when we say that we have plane stress, we say that means that sigma z is 0, tau zx and tau xz are 0, and tau zy and tau yz are 0. So this will significantly simplify our problem, because now we will only have 3 unique stress components in the xy plane. Again, we will see shortly that tau xy and tau yx will have to equal each other for equilibrium. So let's go ahead and take a look at how we determine that. So when we reduce this now into a two-dimensional xy plane, we see our stress element is now just the square. And we have sigma x, we have sigma y, and then we also have tau xy. Again, I will put these stresses in the positive sign convention. So My sign convention has tension positive, so sigma x and sigma y exhibit tension behavior. And then tau xy is on the right hand face moving upwards, so that's on the positive x plane in the positive y direction, or on the positive y plane in the positive x direction for tau ix. You can also think if it's on the negative y plane in the negative x direction, it's like two negatives make a positive. So that this is the shear convention that I will use for the positive shear convention I will use. So if you just want to have this picture in your mind when we talk about, this is positive sign convention, if you just have this picture in your mind, it might help you determine in the future whether or not sigma x sigma y or tau xy is indeed positive or negative. Now I told you that tau yx has to equal tau xy from equilibrium. So I'm going to sum a moment about point A that I've drawn on this square. Now remember, when we sum moments, we have to use forces. So I can't just use stresses times distances. Moments are forces times distances. So I have to first convert my stresses back to a force. So remember, from sigma equals P over A, or if we rewrite that for the force, we can get that the force has to be sigma times area will give us force. Right now I'm looking at the right hand sigma x arrow. That is a distance of dy over 2 from my point A. And again, I'll take counterclockwise moments, summing my moments as my positive direction. If I consider the left hand arrow, I then get a negative sigma x times A times dy over 2. Then if I look at the top arrow pointing upward, I will get a negative sigma y times A times dx over 2, plus sigma y times A times dx over 2 for the bottom arrow, plus tau xy dA times dx for the left-hand shear arrow, minus tau ix times A times dy for the bottom shear arrow. And then my other two shear forces intersect my point at A, so they don't create a moment about point A. And so I set all of this equal to 0. So hopefully you can see that these first two terms cancel, the third and the fourth term cancel with one another, and that leaves us with just tau xya dx minus tau yxa dy has to equal 0. If we say that dx equals dy because we're dealing with a square element or very small numbers, then when we continue to solve this, we can cancel out the areas, we can cancel out dx and dy, and we're left with the fact that tau xy has to equal tau ix. So this is a relatively simple proof of showing how those shear forces on opposing surfaces, adjacent surfaces, have to be equal to one another in magnitude. So hopefully that was helpful. Let's go ahead and talk more about plane stress.
What's that? Did you hear that? I think Megastrain is on his way. I gotta get out of here. Here, take the all-stress cube. Quick, transform, transform. I think he's gone. You lucky out on that one. Seems like we're going to have to fully develop our force, sigma prime, to combat the evil Megastrain. Well, convenient enough. I feel like this is exactly what we want. When we take a look at this, we got a nice triangular block. And this is going to help us greatly when we talk about 2D stresses, right? We don't want to know the stress in the x and the y direction. We want to know what's happening on some random arbitrary plane. Why do we want to know what's happening on this plane? Well, we want to be able to transform our stress into any direction, right? Because the stress could be maximum on some other direction than the xy plane. So it's very important that we know how to figure out what those maximum values are. And so I think if we can fully develop sigma prime on this cut of the element, we'll be able to get to the bottom of this and ultimately defeat Megastrain.
As our hero sigma prime indicated, we need to come up with a method of calculating the stress on an arbitrary plane. So what we'll do is we'll make a cut in our element at some random angle, and we want to draw a free body diagram of this wedge. And in fact, this is the wedge that sigma prime transformed into during that last clip of the video. We're going to follow all the rules for free body diagrams as we draw this wedge. I want to indicate the area, the surface area on which our sigma prime, or the sigma in the x prime direction, will act or will be normal to this surface. So I shaded it here in blue, and I want to refer to this as dA. So this wedge will become a differential element, dA, or just that dA is the area of the shaded blue surface. Also on my free body diagram, I need to have my other forces, or in this case, I have stresses acting. So I have a stress in the x direction that's acting towards the left. I have a shear stress, tau xy, acting down and across, or to the left. And I also have sigma y acting down. What we're trying to determine is an equation for sigma x prime and for tau x prime y prime in terms of the other stresses that we know. So for these two prime stresses, we want to come up with an equation that will relate the three stresses we already know, sigma x, sigma y, and tau xy. We want to use those three stresses that we know to come up with an equation for these other stresses that are on a rotated plane. All right, now I called this a free body diagram because it's kind of this little wedge, but remember, free body diagrams have to have forces, and these are stresses, not forces. So I'm going to more accurately depict a true free body diagram on the next page in the notes, because ultimately we're going to use equilibrium, which requires a sum forces to solve. So I'll replace my stress in the x prime direction with a normal force, N, in the x prime direction. I have a shear force, S, in the y prime direction. And then I'm just going to replace the other stresses with forces, and I'll label them F1, F2, F3, and F4. And so I'll just kind of work myself counterclockwise, F1, F2, F3, and F4. All right, so this now is a good free body diagram because I'm down to having my forces on this block. Now, if I'm going to get forces, I need to translate my stresses to force. And again, we recall that our general equation for stress, P over A, or force over an area, well, then we can rewrite this in terms of the force to get that the force has to equal stress times area. So we're going to take the stresses in the three-dimensional wedge at the top of the screen, and we're going to translate all those stresses into forces that we can use on the 2D free body diagram that we have at the bottom of the screen. So our force N in the normal direction will be sigma x prime times dA. The shear force S will be tau x prime y prime dA. Now F1 will be sigma x, but now we need to multiply by the area over which sigma x is acting. And that area is going to be dA cosine theta. So remember, we define dA as the area along the hypotenuse of the wedge. So we then need to take dA times cosine theta to get the area of just the vertical portion of the wedge. And likewise, the bottom part of the wedge will be dA sine theta in terms of area. I can keep going. For F2 will be tau xy dA cosine theta, F3 tau xy dA sine theta, and F4 sigma y dA sine theta. Alright, so I've now translated all my stresses to forces so that I can do equilibrium. Now, you can sum forces in the x direction and some forces in the y direction if you'd like, and you would get two equations and two unknowns. The unknowns being n and s. I'm going to instead sum forces in the x prime direction. That way I only have one unknown variable. So summing forces in the n direction, I get my force n. My shear force, because it's perpendicular to that direction, does not contribute any components in the n direction. Then I have to look at F1. So F1 looks like it's going to be in the negative x prime direction, and the component there is going to be F1 cosine theta. So hopefully you see that. If not, I would suggest you review your statics to make sure you can get components of forces easily. So this gives us a negative F1 cosine theta. We can do the same thing for all the other forces. I remember that if F1 is cosine theta, then F2, its transformation will have to be sine theta. That's also going to be in the negative x prime direction. F3 is also in the negative x prime direction. It's going to be negative F3 cosine theta minus F4 sine theta equals 0. All right, I could now solve this just for my value n, but again, n is in terms of stresses. All of these forces were in terms of stresses. So I want to substitute all of the stresses, the 6 stresses in the upper right-hand corner of our page. I want to substitute all of those forces in terms of stresses into this equation in the sum forces in the x prime direction. If we do that, we'll see that dA will cancel in all the terms, and then we can start rewriting the equation as such. So n is sigma x prime. I'll bring that to the, keep that on the left-hand side of the equation. I'll bring all my other forces to the right-hand side. F1 is sigma x dA cosine theta times cosine theta, so we get a cosine squared theta. So we have sigma x cosine squared theta. And you can keep doing the algebra, and you'll get the rest of the results of this equation. Next, we can rewrite these equations using the half angle and double angle formulas. And we're basically just going to rewrite this equation into another form that we'll actually be using in the next lesson, mainly when we look at something called Moore's circle. All right, so we can rewrite sigma x prime, and it is equal to sigma x plus sigma y over 2 plus the quantity of sigma x minus sigma y over 2 times cosine 2 theta plus tau xy sine 2 theta. All right, so we've successfully done the transformation. We could go ahead and sum forces now in the y prime direction or in the s direction. And we could develop an equation for tau x prime y prime just like we did for sigma x prime. And I've gone ahead and just listed them there. If you'd like to go through and do that some forces, you're welcome to, and you can show the algebra will prove those formulas. All right, what does this mean? So when we took our element out of the xy plane and we put it into a new coordinate system, x prime, y prime, we needed to transform all of the stresses into this rotated coordinate system. And again, the reason we do this is because when we first look at an object, we can't necessarily determine on which plane we would expect failure. By developing these stress transformation equations, we will then come up with a tool that we will be able to find what planes have the maximum and minimum forces, and those planes might be where we expect failure. So now we have a way of coming up with sigma x prime and tau x prime y prime. The problem is we did not come up with something for sigma y prime. So we have two options here. We can go back to our wedge, and we could cut our wedge a little bit differently, and we could do everything so that we could then formulate sigma y prime. But I think there could be an easier way, because if we look at our block, sigma y prime is the same as sigma x prime, but it's off by 90 degrees. So we can then use the sigma x prime equation, but instead of using theta in the equation, we have to plug in theta plus 90 degrees. And then once we plug in theta plus 90 degrees into that sigma x prime equation, we'll have to do a little bit of algebra, maybe a little trigonometry to use some of our identities, and we will be able to reduce sigma y prime equation into what we would want to use for our calculations. So I just want to go ahead and get this information down, and then we will copy sigma y prime into the box, and you can go ahead and just copy it as it's given there on the screen.
Thanks for keeping the all stress cube safe. Let me see it here real quick. Alright, so we now have an ability to get from this block in some arbitrary XYZ plane to some rotated plane where we can calculate the stresses. So this is great because in some systems maybe the max is in the X or Y or Z plane, but in other systems it's not. And so this formula is going to help us get there. Alright, if you want to know how to find the maximum, we can think back to calculus, or I'll see you in the next video.